my name is Jessica, and welcome to the Vegas PBS STEAM Camp Science Lab. STEAM stands for Science, Technology, Engineering, Arts, and Math. And while it may seem like these are just subjects we learn in school, it's way more than that. STEAM helps improve our lives and our community. Today, with the help of experts, we are going to learn about the STEAM that is all around us in Southern Nevada, which you might have never noticed before. Then I'm going to show you some fun activities you can do at home to learn more. Now, we just need a question to investigate. That sound means I'm getting my first video call of the day from my friend Carter.
Hi, Jessica.
Hi, Carter. What question would you like to explore on today's show?
My question is, how do Thunderbird jets fly so fast?
Thanks for your question. Let's visit the U.S. Air Force Thunderbirds at Nellis Air Force Base to help us answer that question.
Hey kids, my name is Major Michael Brewer and I'm Thunderbird 4, a Thunderbird pilot on the United States Air Force Thunderbirds. I became a pilot when I was about 10 years old when my parents took me to do an introductory flight lesson at the local airport. I went up for about 30 minutes and from there I was hooked forever. A pilot is somebody who flies an airplane. And as a Thunderbird pilot, I fly airplanes in demonstrations for the United States Air Force. As a pilot, I fly the F-16 Fighting Falcon, which is a military fighter jet.
Hello everybody, my name is Tech Sergeant Jonathan DiMaggio, and I'm a Quality Assurance Inspector here at the Thunderbirds. Right now we're at the nose of the aircraft. Our aircraft produce a lot of air resistance and drag, and that's why we have a sleek aerodynamic design to help reduce that. Let's check out the intake. The engine is responsible for thrust and forward movement of the aircraft. And basically, the main ingredients of the engine is air, and it's ingested in here in the intake, compressed and shot out the back. This is our exhaust system. We talked about the intake where the air goes in. This is where the air comes out. And this nozzle closes and opens to help speed up the thrust of the aircraft. And this smoke oil system right here is where we produce a little bit of oil. It mixes with the exhaust and helps produce the white smoke that we have in our air show. These are the wings of the aircraft. They spanned about 30 feet long, and the front and the back of the wings mechanically move to help slow down or speed up air for lift.
Being a pilot is awesome. I get to fly the aircraft upside down, right side up, go really high and really fast. The F-16 is capable of flying over 2 times the speed of sound and over 40,000 feet. As a Thunderbird pilot, we fly between 18 inches and 3 feet apart. While I'm flying, we pull 9 Gs, which is 9 times the force of gravity on your body. Flying close together at only 18 inches apart, we're concentrating very closely on the jet that's right next to us, even at speeds of 450 miles an hour. To withstand the forces on my body while I'm flying, we need special equipment. So let's talk to Aircrew Flight Equipment, or AFE, to learn more.
Our aircrew have to wear a lot of gear. As you can see over here, we have a G-suit, which helps with our Gs. We have a helmet, and we also have a harness. This anti-gravity G-suit is something that our pilots wear every day. It's one piece of many. What it is a pair of pants that the pilots put on in the aircraft. It fills up with air as they're pulling Gs. G-forces multiply your body's weight, which makes your blood pool in certain areas of your body. This decreases that effect. The next piece on our aircrew's ensemble is the harness. What this does is it hooks you into the parachute. So if the aircrew were to eject, this is what will attach them underneath their canopy. Next, we have our Crew 120. First, we have where it hooks into the aircraft to provide our aircrew with oxygen. Next, we have our emergency oxygen, which just in case the aircrew does have to eject, would provide them with oxygen as they are over 14,000 feet. Last, we have where our aircrew plug their oxygen masks into to provide them with oxygen throughout their entire flight. This helmet not only provides our aircrew with oxygen throughout their flight, but it also has a tensioning device in the back, similar to the G-suit, that make sure that when the aircrew is pulling G's, that the mask is tight and secure to their face.
Hello everyone, my name is Staff Sergeant Ryan Jackson. I'm an avionics systems technician by trade, and today I'm excited to tell you a little bit about what goes on inside the cockpit. One of the first things I like to talk about is the throttle grip, which is kind of like the gas pedal of your car. As you move it forward, you push more gas into the engine to make the aircraft fly faster. And over here, we have the side stick, which is kind of like the steering wheel of your car. As you pull it back, you can make the aircraft go nose up. As you move it left and right, you can make the aircraft do barrel rolls. And up here, you have the airspeed indicator, which tells you how fast the aircraft is going. And then over here, we have the altimeter, which tells you how high or low you are in the sky.
I love being a pilot because of the freedom you feel while you're flying an airplane is like none other. If you want to be a pilot, make sure you do very well in science, math, and technology, and do really well in your studies at school. You can start flying at a young age, as early as 9 or 10 years old with a flight instructor. And at the age of 16, you can fly an airplane all by yourself. And at 17 years old, you can even get a pilot's license and fly other people with you. So it's never too early to start.
Thanks, Thunderbirds. Let's review what we learned. Thunderbird pilots fly at speeds up to 450 miles per hour. The jets have an aerodynamic design, including a pointy nose, which reduces air resistance or drag. To thrust the jet forward, the engine takes in air, compresses it, and shoots it out the back through the exhaust. The wings of the jet produce lift to move it upward toward the sky. Flying at high speeds produces G-forces, which multiply the force of gravity on the pilot's body. To withstand these forces, pilots wear a G-suit, which inflates to prevent blood from pooling in certain areas of the body. Now, I'm excited to think like a scientist to learn more about how planes fly. How can I use what I learned to fold and launch a paper airplane that flies fast and far, just like the F-16 Fighting Falcon? So here's the plan. You are going to fold 4 paper airplanes and compare and contrast how one small change to the design affects their flight. To do this, you will need 4 sheets of paper. All of mine are the same except for one. I'm going to fold one plane with heavier construction paper to see what happens. Be creative and see what kinds of paper you can find in your home. You will also need paper clips to add weight, a tape measure, a ruler, a pencil, a data collection chart to record your observations and results. First, choose one design for all of your paper airplanes. To make a basic airplane, fold the paper in half the long way, like a hot dog bun, and then open it back up. This middle crease will be your guide. Fold the top 2 corners in to line up with the middle crease. Now repeat. Grab the outer corners, line them up with the middle crease, and fold. Now fold the plane back in half. Create a wing by folding down the top edge to line up with the bottom. This is where a ruler comes in handy. Press it down along your line to make it nice and crisp. Then flip the plane over and repeat to make a wing on the second side. Now throw it and observe. Does it fly straight or curvy? Write your observations on your chart. And when you've had enough practice time, throw your airplane and measure the distance it traveled. If you don't have a tape measure, you can measure using your feet. Just be sure to walk heel to toe in a straight line. Throw your plane 2 more times and record the distances it traveled on a chart. When you're done, fold another airplane the same way, but make one change. Maybe use a heavier or lighter paper. Bend a wing, fold some flaps up and down on the back. Add a paper clip. Change the way you throw, or make a very tiny version of it. At the end of the investigation, look at your chart. Which airplane flew the farthest? Did the kind of paper matter? Did the way you throw it make a difference? Do bigger or smaller planes fly farther? And what happened when you added the weight of the paper clips or bent a wing? Now, let's check in with Carter, who's doing this activity at home right now.
Hi, Jessica. Today I'm going to talk about my 2 paper airplanes. And my 2 paper airplanes, one of them has a paper clip on them, which makes it heavier. and the other one doesn't, which makes it lighter. I think this paper airplane's better because I added this clip to the front of it, and it makes it heavier when you throw it. I measured my paper plane by counting my steps. The heavy one flew farther than I thought. My next paper airplane design is going to be a smaller model of the airplane I have with a paper clip at the end.
Great job on your investigations. An important part of being a scientist is sharing your work with others. Visit our website at vegaspbs.org/STEAMcamp to submit videos or pictures of your results to us at Vegas PBS with your grown-up's permission. Or ask a grown-up to share it with us on social media by tagging at Vegas PBS. Keep in mind, if you are submitting a video, make sure we can see what you're doing and hear what you're saying. Also, you'll want to keep it to about 1 minute or less. We will post some of your projects on our website, and if yours is selected, we'll mail you this awesome PBS Kids bag and a new book. When you visit our website, you'll also find a copy of the chart we use to keep track of our data and links to PBS Kids shows and activities to learn more about flight. Now, let's visit the library to discover books you can check out to help you learn more about this topic.
Hi, my friends. My name is Miss Joanna, and I'm a children's librarian at the West Charleston Library. I heard you learned amazing things about the Thunderbirds, and I sure learned a lot. So I wanted to share a few books that you can check out at your local library. The first one is called Airplanes, Soaring, Turning, Diving by Patricia Hubble. These different types of planes here. We have propellers, rotor planes, ones that you can fly with your hands. It's pretty cool. And the best part I love about this book is it shows our heroes, just like our Thunderbirds, soaring and doing air shows for all of our friends. I heard that you also did a challenge on your paper airplanes where you changed different things to see how they flew. If you want to take that a little bit further, we have this really cool book series by Marie Buckingham. It shows you all the different ways that you can fold paper airplanes, and they increase in difficulty. So you can pick up one book, work on your skills, and then advance to the next. I hope to see you soon.
Welcome back to the Vegas PBS STEAM Camp Science Lab. We've already learned so much today, and we still have time left to investigate another question. Here's another caller. It's my friend Royce. Hey Royce, so nice to see you.
Hi Jessica.
What question would you like to explore on today's program?
And I was wondering, how was Allegiant Stadium built?
That's a great question, and I actually know a few engineers who worked on Allegiant Stadium. Let's go talk to them to get some answers.
Kids, welcome to Allegiant Stadium. We're going to show you today how we used math to design and construct the stadium. So how did we use math to design the stadium? Well, we started with a vacant piece of property, 62 acres big. 62 acres sounds like a lot, but you have to fit quite a bit in that. Just the building itself to house 65,000 fans takes up 7 acres. And then you have all this other stuff that needs to fit in the site. 2,400 parking stalls, drive aisles, landscaping, you name it. We had a lot to fit in 62 acres. There was so much concrete used to construct the stadium site that you could build a sidewalk all the way from Las Vegas to Los Angeles, 257 miles. That's a lot of concrete. A lot of measurements to design this site. Here's one example. we had to fit 2,400 parking stalls within the site. Each parking stall is 9 feet wide by 19 feet long. One other way we use math to design the stadium is elevation. Elevation is the amount of feet above mean sea level. The elevation of the stadium is 2,197 feet. Add on top of that 226 more feet and you get the top elevation of the stadium. That allows us to be just below the flight path and allow airplanes to still fly over top of the stadium.
Welcome inside of Allegiant Stadium. We're down here on the field level. My name is Paul Dudzinski, and I want to show you today the grand scale of this building. The building itself takes up over 7 acres of the project site, and there's about 65,000 seats all the way throughout here. When you start to talk about scale and the size and the magnitude of the building, this isn't something we can fit on one sheet of drawings. In the engineering and architecture world, we use what's called scale, where we draw something at a much smaller size than it really is in real life. So this stadium started as a set of architectural plans on flat paper, all engineered on computers using math and scale and proportion. And so through the use of that, we're able to take the massive size of this building and shrink it down and fit it on various sheets of paper. So when we talk about size and scale and proportion, I've got what looks like a ruler here. This ruler is actually an engineer's scale, where we use a measurement of 1 inch to equal various quantities, like in this perspective, 1 inch equals 30 feet. That's the same distance from the 10-yard line to the end zone. That's how we're able to fit a building of this size on architectural plans and drawings.
Hi, my name's Bailey Ruff. I'm a project manager out here at Allegiant Stadium, and I worked on setting up all these seats. There's 65,000 seats at Allegiant Stadium, and we're sitting in just one seating section and one row of that seating section. And each seat needed to have the perfect view of the field. So the architects used what are called sight lines to take the line of sight from your eye all the way down to the field to make sure that there was nothing in the way of your view. Each row in the Allegiant Stadium has a different number of seats in it, and that's because each seating section is a different size, and that has to do with the shape of the stadium. So the shape of the stadium is an oval, and each seating section is kind of like a piece of pizza that fits around the oval. It's like the piece of pizza that you took a bite out of. So that means that the closer you get to the field, the least number of seats you have in the row. So we were able to fit 65,000 seats across the whole stadium, and everybody has a great view of the field.
Hi kids, I got into civil engineering because I love solving problems and I love math. If problem solving is something that you enjoy doing, if you like working with people, civil engineering may be a career for you.
My profession is a construction manager, and I love this job because I get to be a part of cool buildings like this. I get to use math and accounting and problem solving and all kinds of skills to be able to create beautiful projects like this one.
Thanks, everyone. Today we learned engineers used a lot of measurement to design and construct Allegiant Stadium. Measurement helped engineers fit the stadium, parking, landscaping, and drive aisles onto a 62-acre piece of property. Scale helped architects draw plans for Allegiant Stadium at a much smaller size. An engineer's scale is like a ruler that uses proportion, where 1 inch equals a certain length in real life. There are 65,000 seats in Allegiant Stadium. Engineers use sight lines, which is an imaginary line from your eye to the field, to make sure each seat has a perfect view. Wow, that was amazing! I never realized there was so much math involved in creating a building. Now it's your turn to think like an engineer and build a scale model of your bedroom. It'll be like an exact copy of your bedroom, just a smaller size. To do this, gather your materials. You will need at least 3 cereal boxes, Cut open your cereal boxes to give you flat pieces of cardboard. You will also need a pencil, ruler, tape measure, some markers, scissors, a few sheets of construction paper, glue, and tape. The first step is to draw a floor plan on the inside of a cereal box. A floor plan is what your room looks like when you look down on it from above. To make one, you will need to measure your bedroom walls. Start with the wall farthest away from your door. Ask a grown-up for help to find the width of that wall in feet using the tape measure. Then you will use your ruler to shrink down every foot in real life to 1 inch. To do this, place your ruler near the top of the box. I like to line mine up with the fold on the cereal box to help me draw a straight line. Remember to use the side with inches, which are the large numbers. Every inch on your ruler is going to be like 1 foot in real life. So, if your wall is 10 feet wide, you will need to draw a line along the ruler that is 10 inches long, just like this. If your wall has a window or door, add it to your floor plan. Using the tape measure, work with your grown-up to measure where the window or door starts and stops, to the closest foot. Then mark these 2 numbers on the line you just drew. So if the window in your room started at 3 feet and ended at 7 feet, I would draw 1 mark at 3 inches, and then another one at 7 inches. Ta-da! There's my window. Now use your tape measure to find the length of your next wall in feet. Then draw that wall on your floor plan in inches, just like this. Repeat the process until you've measured all of your walls, marking any other doors and windows. When you are done with your floor plan, cut it out. If you want to take this activity further, you can use your floor plan to create a 3-dimensional scale model of your bedroom. All you'll need to do is add walls. Line up a piece of cardboard next to each wall on your floor plan and mark the length using your ruler and pencil. Then cut it to match. Make sure all of your walls are the right height though. Ask a grown-up to help you measure the height of each of your walls with the tape measure and use your ruler to mark the height on the cardboard wall. Remember to use scale and mark it in inches. Mark the height in a few spots by sliding the ruler down the cardboard. Connect these marks to make a straight line, just like this. After you've created all of your walls, you can even add windows and doors out of construction paper and glue them to the inside of your model. Use scale to make sure your windows and doors are the right size and line them up with where they are marked on the floor plan before gluing. And connect them together with tape around the corners. Now, let's check in with Royce to check out how he created his scale model.
Hi Jessica, this is my model room. First I measured my room and my largest wall was 13.5 feet. Then I made my scale ruler, and which went up to 14 feet. And my largest number that I went up to was 13.5 feet. Then I made a 1/2 inch, which equals 1 foot. And I'm not quite done yet, but I want to add a dresser here and a picture here.
Thanks for showing us your engineering skills. And kids, I want you to share your scale models with me. You can submit a picture or video of your finished product through our website at vegaspbs.org/STEAMcamp with your grown-up's permission, or ask your grown-up to share it with us on social media by tagging @VegasPBS. And remember, if you're submitting a video, make sure we can see what you're doing and hear what you're saying. Also, try to keep your video to 1 minute or less. We will select some projects for our website, and if we choose yours, you'll get this cool PBS Kids bag and a new book. When you visit our website, you'll also find links to PBS Kids shows and activities to learn more about scale and architecture. Now, let's visit the library one more time to discover books you can check out to help you learn more about this topic.
Hi everyone, I'm Miss Marisa from Summerlin Library, and you just learned all about architecture and architects. And you got to see the Allegiant Stadium. Isn't that a cool building? Can you imagine what it took to build that building? If you're still interested in learning more about architecture and architects, I grabbed a couple books from the library to share with you. The first one is Iggy Peck, Architect. Iggy has been an architect his whole life. He even built a tower in only an hour using nothing but diapers and glue. I don't know if I'd want to see that tower, but it sounds interesting. One day on the second grade field trip and picnic, disaster struck. And Iggy's architecture skills were needed. Was he able to save the day? I don't know, you'll have to check out the book to find out. Another book I picked out is the Illustrated Atlas of Architecture and Marvelous Monuments. This book covers almost every amazing building ever made in the world. And it goes by region where you can learn measurements of each building, how it was built, the ideas behind them, with beautiful illustrations. So come to the library, come see me, check out these books, and I'll find you some other books about architecture. I'll see you soon.